Welcome to Lecture 4 of the course Introduction to Data Science. So today we are going to talk about a very basic data science technique, that's the use of regression. This is another example, just like decision trees, of a very simple supervised learning approach, and we use this to explain more sophisticated techniques like neural networks and also SVMs in later lectures. So what is the plan for today? Today I first explain you simple linear regression as the basic idea, and then I will stepwise start to extend it. First we will have one descriptive feature and one target feature, both continuous. Then we move to the setting where we have multiple descriptive features, and then we will talk how we can read and interpret these results, and then we move to the categorical domain. So we are looking at how can we either transform variables from, let's say, categorical into, let's say, numerical, or how can we handle them directly. And this leads to the notion of logistic regression as a classification technique with categorical target features. At the end I will also briefly talk about what happens if we have multinomial target features and we look at the nonlinear case. But this will be very high level. Okay, let's start with the basic idea of regression. So the basic idea of regression is that we start with an initial solution, we compute its error, and then we try to stepwise reduce the error. That is visualized here if I switch on my pointer. Yeah. So we start with a certain error and we try to stepwise reduce the error until we no further can reduce the error. This is a kind of very generic approach that applies to regression, but also applies to many other techniques. So the basic idea is that we have an error function and we have a way to update, let's say, our solution in a stepwise manner to get better and better solutions. So in this course you will see, let's say, three types of error-based learning techniques. Regression, which is in this lecture. We will also look at support vector machines, which are very similar to logistic regression. That will be in the next lecture. Let's say in the lecture thereafter we will look at neural networks. Other techniques which are based on error-based learning are things like genetic algorithms and other evolutionary approaches. All use the principle that we start with an initial solution and we try to improve this initial solution by updating it. And we can do this in a, let's say, brute force approach, what is done basically in genetic algorithms, that you have something like survival of the fittest, or it's something, let's say, very specific and very targeted, like what we will see in linear regression. So what's the basic idea? To explain the basic idea, I look at a very simple situation where we have only one descriptive feature, indicated here by the y-axis, by the x-axis, and we have one target feature indicated by the y-axis. And we would like to find the relationship between the descriptive feature and the target feature. And we assume that it is a linear function, as indicated here by the black line. And what we would like to do is we would like to find the line, the regression formula, that is minimizing, let's say, the distance of the different observations from this line. We would like to stepwise minimize that. Here we only have one descriptive feature, but of course later we will see that we can apply that to any number of descriptive features. So we are using continuous features, both as a descriptive feature and as a target feature, Later we will extend, let's say, a regression to also capture categorical features. So we are following the opposite path of the path that we have followed for decision trees. When I explained decision trees, we started with categorical features, and then I showed you how it could be extended and refined towards continuous features. Here we will do exactly the opposite. Both decision trees and regression, however, are both supervised learning techniques. So that's the setting, and we start with the simplest case, linear regression, and we also, for the moment, assume that we have just one target variable and one descriptive variable. So in this example, we would like to, for example, see the relationship between size and rental price. This is a data set taken from this book, the book that is kind of the core book that we use at this point in the course. And the basic idea is to find a linear function linking size to rental price. So the assumption could be that the bigger the apartment is that you would like to rent out, the more money that you will get. So I remove the other columns and I just look at the column size and rental price. And now we want to find a linear function between expressing rental price in terms of size. So the function will have the format that we see here. So rental price is equal to B plus A times the size, where B is a constant and A is multiplied with the descriptive variable that we have. So a possible solution for A and B could be that A is 0.62 and B is 6.47, as you can see here. So the question now, is this now a good description? Is this a good function showing the relationship between size and price? And we can basically do that by measuring the error. So what is the general problem? And we will come back to this later. The general problem is, of course, that we have multiple descriptive features. In our data set, we have a target feature with concrete values. We have concrete values for all the descriptive features, and we would like to make a prediction, that's a function, based on the descriptive features that is telling us what is a good prediction for the target feature. So we will come back to this representation in a minute, but you can think of a data set as a table. Note that normally we write a target feature at the end, at the last column. Here it is listed as the first column, but nothing new for you. We have n instances and m descriptive features. To keep it simple, as I mentioned before, we just drop this and we assume that we have just one descriptive feature, so that we can visualize it nicely like in a graphical way. So again, here size is our descriptive feature, rental price is our target feature, and we would like to find the relationship between both. So this is the function that I showed before. So it's basically plotting rental price in terms of size. I think this is very easy to understand. And this is one candidate solution, and in principle every line in this diagram would correspond to a possible solution. And so if we kind of show the general notation, is then this is the predicted target value that is equal to W0 plus W1 times D1. And we can do the mapping of this, and so this is what we would like to predict. And then we have these weights, so we have like the constant, always called W0, and we have the weight of the, let's say, first descriptive feature. But as mentioned before, there could be any number of descriptive features, but here we only have one. That's why the formula looks like this. And D1 is the value of the descriptive feature. So I think this is very simple, but this is just to make you get used to the notation that I will be using on the slides and that you will also find in the book. So any value for W0 and W1 corresponds to a possible solution. So here I'm plotting like different candidate lines under the assumption that W0 is equal to 6.47. So we fix this and we just, let's say, change the angle of what we are looking at. Of course, we could also vary, let's say, W0, but this is how you get an idea of how these functions could look like. And now we want to pick the line, and we have infinitely many possibilities. We would like to pick the line which has the smallest error. And the error is defined as the distance from the points to the line that is describing the relationship. Here this is visualized, so here we see a possible candidate. The circles corresponds to the different instances that we have. It is describing the target value and the predicted value. So for example, if we look at this point, we estimate a rental price that is higher than it is in reality. If we look at this point here, then we are estimate a rental price that is lower than the actual value. So we can see that sometimes we make a right prediction, sometimes we are, let's say, too high, like for example with these 2 points, and sometimes we are too low, as with this point and this point. So we can simply measure the distance from every point to this line, that is the error. And what we typically see is that we are not simply computing the sum of errors, that is one possibility, but the default formula that is typically used when people use regression is that we take the difference between the predicted value and the real value in our data set. We take the square, we sum that, and we divide that by 2, as we can see here. So this is the situation that we have any number of descriptive features. So this is a vector. This is the situation that we just have one feature. So this is the predicted value. This is the real value. We take the difference, we square it, we sum it over all the instances, and we divide it by 2. So this looks very particular, and in a minute we will see why this is the case. So here is the process. So for each instance, we compute the error, the difference between the predicted value and the real value. Then we square the error, we compute the sum of all these squared errors, and then divide it by 2. There are different ways of measuring the error. This is what I just explained, that is the sum of squared errors. We can also look at the mean squared error. So then we take again the differences, square them, sum over all of them, but then divide by the number of instances n. We can take the root of this value, and just as you're used to statistics, that we often also take the square root of the variance to get the standard deviation. We can also look, and perhaps this is the most logical thing for you, but in a minute we will see why we typically do not use that. We could also take the absolute error, so we simply take the difference between the real value and the predicted value, we sum over these and divide it by n, and we get the mean absolute error. Let's take a look at some numbers examples. So if we take the sum of squared errors and we fill in the values, then this is what we get. So if we look at the first point, we predict this value, the value that we predict is exactly the value that it is in reality. So we have the error is 0 and we square it. Here the predicted value is higher than the real value. So if we take the real value minus the predicted value, because it is higher, we get a negative number, that is minus 2. The third point, again we have no error, 0 to the power 2. And then if we take a look at this point, this is the real value, if we look on this dimension, and this is what we predict, as we're at this point here. So again, we take the real value minus the predicted value, and that's a positive number 3. So we have 3 squared, and then we divide that by 2, leads to 6.5. Already, and I will come back to that in a minute, why does this look like this? That is if we, that is to do that the derivative of this sum of square errors has a very simple form, and that is due to this relationship. That also explains the half, because we have here to the power 2, and then we have 2 times half, and then it disappears. Basically using this formula. As I said, I will briefly come back to that, but I'm referring, let's say, to your high school mathematics here to understand why we are doing this. The main reason is that it has an elegant derivative that has nice properties. We can also look at the mean squared error. Then these values are the same, and we divide not by 2, but we divide by 4, because we have 4 data points. Simple. We can also take the root of the mean squared error. Then we get this value, and then the square root. That's easy to see, I think. And I hope that the intuition from statistics, looking at the difference between variance and standard deviation, helps you here. And we can also look at the mean absolute error. So now we don't square things, but we simply compute the error. Whether it's positive or negative doesn't matter. Then we divide by 4, and then we get this. So all lead to different values, and in the remainder we will use the sum of squared errors. And why is that? The reason is that it has a nice derivative that has nice properties, and that is easy to compute with. So here is let's say a short refresher of your, let's say, high school mathematics on how to compute derivatives. So alpha is a constant here. If we take the derivative of a constant, the outcome is 0. If we have alpha times x to the power n, and we take the derivative, then it looks like alpha times n times x to the power n minus 1. That's what we just applied. If we take the derivative of a sum of two things, we can simply split it. If c is a function that includes a variable x, then the derivative of some constant multiplied by such a function, again depending on x, looks like this. So these are the basic rules. You cannot always apply these, but often you can use the chain rule to compute the derivative. So the basic idea of the chain rule is that if I can rewrite it somehow as a function of a function, and this could be repeated as many times as you want, then we can apply the chain rule. So the derivative of this is the same as computing this. So first the derivative not of x, but of this function gx times the derivative of just gx. If I show it in an example, perhaps then it is more clear. So if I compute the derivative of this, then I have this part to the power 2. Then I can take the derivative of my original formula, but my x is now replaced by this. Then we get this expression times the derivative of x to the power 2 plus 1. And what I can now do is I can apply the rules that I just had, and then this is what I get. So as I said, if this is difficult for you, please take a look at Appendix C in this book, or look at, let's say, your high school mathematics book. So this is visualizing the derivative. So this is the function fx, with the solid black line. And here the dashed line is showing the derivative. So here it's negative because we are going down. Then there is like a plateau, that the derivative is 0. And then it's going up again. And the bigger the x, the faster this goes. So this derivative is also going up. Just fill out some values and you understand that this is actually the correspondence. So that's a basic refresher showing, let's say, how to compute the derivative of a function. Often we look at situations, so if we have multiple descriptive features, then of course we have multiple variables, and then we take partial derivatives, and that basically means that we keep all of the variables constant except one, and this one we are varying. So if we take the partial derivative using variable x, then this comes out, and this, you can understand this because this basically corresponds that you consume for the moment that y is constant. Yeah, so this part is dropping, this part becomes 2x, the 2x becomes 2, the 4y will simply disappear because it's a constant, the plus 2 will disappear because it's a constant, and this minus xy, y is a constant, so that is remaining. This is looking at it from the perspective of variable y. Now we keep x constant and we just vary variable y, and this comes out. So again we have this is rewritten to minus 2 times y, this disappeared, this is reduced to 4, and this minus xy becomes minus x. Very, very similar to the situation before. Please note that the intuition of derivatives means that if I make a small change in one of the variables, for example x and y, what is the effect on the function? Making a very small step, how does fxy change in a positive or a negative sense? This is visualizing this, so here I'm showing let's say this function that we just looked at, and here we look at the, let's say, the two partial derivatives corresponding to that. And if you look at it closely, you can clearly see that, for example, if we are here, if we are somewhere here, and we are, let's say, reducing the x value, then what we see is that the target function is going down, and that's what we see here. And so please fill out some numbers and you will understand what I mean. So now back to our original problem, and I'm now going ahead a bit, but this is that you understand why we use this particular error function. If we compute the derivative of the partial derivative of this, varying a particular descriptive feature j, then the derivative of this corresponds to this. And then you can see that it is elegant. You also see that this half disappears because of the 2 that we have here. Note that I'm already considering, let's say, multiple descriptive features. Here I'm focusing on one labeled j. The I in this is again referring to the instances. So in this example there are 4. And we only have one, let's say, descriptive feature, so our index j would be equal to 1. So now we go back to, let's say, and now we understand again what derivatives are, etc. We understand why we have this error function. Now I show you different linear functions, and I'm showing you what is now the error the sum of squared errors for all these different lines. And if we now look at the example lines that we have here, then we see that this one has the lowest error. And this one is corresponding to this line, and this line is the lowest value for the error that you can get for this particular data set. Note, because we are trying to fit, let's say, points that can be completely random in this, let's say, two-dimensional plane, it doesn't need to be the case that the error can be zero. It can be that we cannot describe this data set using a linear function. But this is the minimal error value that we can get. So if we are plotting the error, this error function that we looked at before, and we plot that in terms of let's say, the different candidate values for W1 and W0, and we plot this, then this is what we see. And we basically try to find the lowest point, let's say, for all possible combinations of W0 and W1. And what you see is that the surface of this function is smooth, and that allows us to do the magic that we will do in a minute. So a possible solution would be simply to use a brute force approach. We would simply try many different candidates for W0 and W1, but of course this is not feasible, because we may have many variables, and the variables may span, let's say, a large spectrum of possible values. So this doesn't work, so we need to be smarter, and that is why we are using this particular error function, because this surface is smooth, we can basically just walk down until we have found the lowest point, and if we find a point where we can no further improve, we know it is optimal. Yeah, so if we are at the lowest point, then we know that the partial derivatives will be equal to 0, because we can walk in no direction, lowering the error. So that corresponds to this equation. So if we find the solution for W0 and W1 such that these partial derivatives are equal to 0, then we have found the optimal, let's say, position with the lowest error. So how does this work? Well, this can be explained very easy. If the surface that I just sketched, if that surface is convex, then we can simply take the derivative. We know in which direction that we can walk down, and we just continue to walk down until we have reached the lowest point. And any, let's say, local optimum, local lowest point is also a global lowest point. So metaphorically, I'm showing here like an area that I really love. It's in the Dolomites. And like, if the Dolomites would be, the terrain would be convex, which is not the case, then we would always, if our car is at the lowest point, we would always find our car, no matter what we do, if we just continue walking down. That's the basic intuition that you should have. So what does convex mean? That means that if I have such a function and I connect, let's say, 2 points, then they cannot cross the function somewhere else. And this is essentially the same as stating that a local optimum, so a value that cannot be locally improved, is also globally optimum. So this is convex, this is not convex. And this is what I just said, that if things are convex, then a local minimum, which we can locally no longer improve, is also a global minimum. That clearly holds here, that doesn't hold here. Because if we are here, we have reached the lowest point, but there is another lowest point, there's another point that is actually lower. So the basic idea of gradient descent is that using the derivatives, we know in which direction the function goes down, and then we take steps walking down our mountain. So if we have a global optimum, we are clear that if we can no longer improve, we have reached a global minimum. If we have a function that does not have this property, then we can get stuck in the local minimum. So the smoothness and the fact that the surface is convex, let's say, is of key importance. As I said, if you understand this, let's say, intuitively, then it's very simple. If we have these properties, then we can find the solution with the lowest error by simply walking down. And the only question that remains is what is the size of the steps that we want to take. So we can take big steps or small steps. What you typically see is that if you apply regression, that in the beginning you take bigger steps, and the closer that you get to the optimum, you start making smaller steps. But all kinds of strategies are possible there. So if we look at gradient descent, and here we are taking steps that may be too big, we can even overshoot our solution. This is the situation when we take steps that may be too small. So we want to somehow balance the step size. There is no, let's say, objective way of doing this, but there are many heuristics that one can apply to do this very fast. So this is showing the situation that because of these properties, no matter where we start with our initial solution, so here I started from 4, let's say, very different points, and if I'm using this strategy of, let's say, gradient descent, then I always end up with this global minimum. And these are, in essence, two visualizations of exactly the same data. So if we look at the example that I sketched before, taken from the book, if we start at some point, then in a few steps we reach the point where the error is minimal. And again, I'm showing it here in two different ways. So the plot that I just showed, these plots, they show the error. So how, using gradient descent, we are making the error smaller and smaller and smaller until we can no longer improve it. That doesn't, however, visualize the regression line, the linear dependency between the dependent variable, between the descriptive variable and the target variable. It doesn't really describe this. That is done here. So in these diagrams, I do not show all the different steps, but I show, let's say, some let's say, intermediate regression lines. So this is my initial regression line, and then using gradient descent, I'm, let's say, changing my weights to lower the error, and then I get this. So in situation 2, the error is lower, then I still know in which direction to walk. I get to situation 3, etc., etc. So in the end, 5 is, let's say, the position where the derivatives are equal to 0. So we can no longer improve because we have found the global minimum for the error. In this last graph, we see the evolution of the error. You can see that also a bit in the images. In the beginning, we have a very big error, and then we gradually decrease the error, but towards the end, it becomes more, we are almost at the optimal value, so it becomes more difficult to make big steps towards improvement. So that was the most simple case. We have just one descriptive variable. We have a target variable. They are both continuous. This is the simplest situation. Now we do something, and I already hinted at it many times. We can also do this for multiple descriptive features, still continuous. I didn't do that because it becomes more difficult to visualize this. So if we look at it technically, then first we just had this part, W0 plus W1 times D1, because we had just one descriptive feature, and we had one estimate for the target feature. Now we can have any number of descriptive features. Here we have M, and this is then the formula that we have. We can rewrite that to this. We have M variables and one target variable. We can rewrite this to this. What we often see is that we have this notation where both W and D are not values but are vectors, and then we can take the dot product. The assumption that we then have, because we have this W0 here, which is not multiplied by a variable, is that we assume that there is a variable D0, which is always equal to 1. And when it's always equal to 1, then the term W0 times D0 is simplified to simply W0 when D0 is equal to 1. So we can rewrite it like that, and then that's what you often see, this dot product. So then we can use a more compact notation, and we can use, let's say, linear algebra to do all the magic for us. I hope this is clear. And the concepts are easy, but the notation may be a bit overwhelming. Now we look at the error function. Again, I'm not changing anything. So what we had before is we have n instances labeled from 1 to n. I is a specific instance, so a specific row in my table. Ti is the real value of the target feature, and this expression is the predicted value for the target variable based on, let's say, the different attributes for the descriptive features. Yeah. So here D, that's why it's boldface, corresponds to a vector, and this vector is equal to m plus 1, where m is the number of descriptive features. So our regression model basically is determining the weights W0 until Wm, and we can simply take the product of these two. So this is my predicted value, and I compare it with the target value. I take the square of the error, I sum it up, and I divide it by 2. Exactly the same as before. So if we now look at, let's say, before we just looked at size, now we also include floor and broadband rate. And now our regression formula starts looking like this. So we have W0 until W3. And so in total we have 4 weights. And we would like to compute the weights in such a way that our error is being minimized. I think this should be pretty clear. If I compute it for this simple data set, then what comes out is that these are the weights that minimize the error for this particular data set. So W0 is equal to minus 1513, W1 is equal to 0.62, etc. So we simply have determined the weights in such a way that we minimize the error. And we are using exactly the mechanism that we also used when looking at just one descriptive feature. So this is now the sketch of the algorithm. You could describe the algorithm as walking down. So you are parachuted into some random initial point. That's what's happening in line 1. And then you repeat the following procedure. You compute the derivatives of the point where you are currently standing. Then you know the direction in which you can improve, and you walk into this direction. And you do that with the speed alpha. So alpha is, let's say, the step size that we are using. As I mentioned before, often the strategy is being used that in the beginning alpha is bigger, and towards the end alpha gets smaller to not overshoot the solution. So we stop if the improvements become, let's say, too insignificant. So you can all imagine that such stopping criteria can be easily implemented. So the key thing is, of course, this step where we are updating the weights. So we have a weight for every descriptive feature, and we have this constant W0. So remember that this was our error function. Here we take the partial derivative looking at a particular feature j. Then this is the function that we have. We have a value like this for each of the different features, and we basically use this to determine in which direction to walk. Yeah, and how fast we walk into a direction depends a bit on how much we can improve using this partial derivative. And note that there is this symbol minus that goes away here because we would like to lower the error. Okay, so this is the machinery. Then the interpretation of the results is very easy. If we have one feature, we can even visualize it. So the interpretation is that for every value of size, we have a prediction for the rental price, and we know how to compute the error. And we are looking for the line that has the least number of errors. So if there is one variable, one descriptive feature, then it's easy to interpret. And we also can interpret that the bigger this value, and the 0.62, the bigger the effect on size. So if I would have a similar formula, and like this weight would be 0.002 or something like that, we would know that the effect of size is very limited when it comes to the rental price. So if we have multiple variables, it's no longer so easy to interpret. So what we now see is that we get this regression formula. It is minimizing the error for our data set, but how should we interpret this? Is it now because this says 0.62 that size is more important than the other variables? What I'm trying to say is that the absolute value of these weights says very little about the impact of that particular variable. And why is that the case? Because the dimensions of these descriptive features could be very different. So that's what I'm trying to explain here. So if we, for example, look at the feature size, we could express the feature size in square centimeters, in square meters. We can use different ways of measuring the size. And of course, this will have a dramatic impact on the weight of this W1 factor. The same as if we look at the broadband rate, it could be expressed using all kinds of different units. If we look at the rental price, we can also express it in dollars, euros, pounds, bitcoins, all kinds of things. So the absolute value of these weights doesn't say very much. So how to handle this? Of course, you could first try to normalize all the dimensions and handling this. But something that is more sophisticated is you could use a significance test. And the basic idea is that you leave out one of the variables and see what the effect is on the error. Yeah, and this can be done using hypothesis testing. I'm not going to explain this in detail. At the end of the slides, you'll also find some more slides that you can study yourself, explaining this in a bit more detail. But the basic idea is that we test a null hypothesis, and the null hypothesis says that the feature that we want to leave out does not have a significant effect on the model. So the null hypothesis is that the feature does not have a significant effect. In other words, with or without the feature, the behavior is similar. And then this null hypothesis is rejected when the p-value is too small. So we test for this null hypothesis, and if it leads to an extremely small p-value, then we reject this null hypothesis. Yeah? And so in other words, this is, as always, in statistical hypothesis testing, the p-value is the probability of obtaining test results as least as extreme as the results actually observed during the test, assuming that the null hypothesis is correct. So we assume that the feature does not have a significant effect, and then we see whether we can reject it because the p-value, let's say, is absurdly small. So we do that, and if we look at our example, then we can compute these p-values obtained by inspecting every individual variable, and then you can see that the p-values for floor and broadband rate are pretty high, and only for size we find a very small value. So the implication is that only size is not rejected. The other ones, like for floor and broadband rate, using this hypothesis testing, we decide that they are not that important. Okay, so that was dealing with the situation that we have multiple descriptive features. Now we change the scenery, and so far we have just looked at numerical features, so continuous feature variables. Now we're going to look at the situation that we have either categorical descriptive features or categorical target features, as you see in this example. So what kind of consequences have that? Can we still use regression? Note that when we talked about decision trees, we worked in the other direction. So we started with the technique that could handle categorical features very well, and then we had to adapt and change it to capture, let's say, continuous descriptive and target features. Here we go the other way around. We try to handle the situation that we now have categorical features. So if we look at categorical descriptive features, so for example, I have energy rating here, apparently having possible values A, B, and C. Then the question is, okay, can we now do regression? Although we don't have numbers, we have these, this categorical feature, energy rating. So one way to handle this is to encode all possible values as a kind of vector, and every, let's say, element of this vector corresponds to a new descriptive feature. So the original descriptive feature, energy rating, is split into three, let's say, separate features, one for every category. So this is the result. So for example, we can now see that the first apartment has an energy rating of C, the second apartment has an energy rating of A, etc. So now again we have, let's say, numerical values, and we can apply regression as before. So we can see what the effect is on this. So that's one approach, and we can just use the machinery. Sometimes this is a bit overkill, So sometimes when we have binary values, it's actually very simple. We can just use 0 and 1. Although we have two values, true and false, we do not need to use to introduce two new variables. We can simply stick to the old one, but relabel true to 0 and false to 1, or the other way around. If we have categorical variables with a clear order, so they are ordinal, for example, excellent until horrible, then we can also put them on a numerical scale. So these are situations where one hot encoding is a bit of overkill. So what are possible issues? So for sure, if we have unordered categorical variables, we cannot map them onto a single number. And we need to use this one hot encoding that I showed before. What is also important to note is that regression will assign values that do not need to be, let's say, 0 or 1. They do not need to be exactly these values. So the variable b in our regression formula could also be 0.66. Although that never happens in the set that we use to learn the regression formula in principle allows for values other than 0 and 1. So that's a problem with one hot encoding. Another problem is that it would even allow that both A and B are 0.66. This is of course not possible because we know that if A is equal to 1, then B is equal to 0 and C is equal to 0. So these dependencies are lost, and making this really an approximation. Also, if we have a categorical feature with many possible values, this may lead to an explosion, because if we use one hot encoding, we need to have a new variable for every possible value. So there are many issues, and that's why there are also, let's say, more refined techniques to tackling this problem. So far, we have only considered categorical descriptive features, not the target feature yet. Now we are going to look at a special situation that we have a target feature that can have two values. In this example, you can see that we have the values plus and minus. They could mean true, false, they could mean high, low, they could mean red, green. So you can think of any, let's say, binary classification. We now do not want to find a formula which is computing the class directly in terms of these, let's say, continuous variables. What we want to do instead is we want to find a line that is basically separating one class from the other class. So here in this diagram we are looking at a situation where we have two descriptive features, numerical descriptive features, x and y, and we are interested, based on x and y, can we now predict what our target feature is, and that is shown here with the name class. So that's the basic game that we are trying to do, and we can talk about the distance from this separating line, and that can be either positive or negative depending on which side of the line you are. This is a bit tricky, but I will explain this in steps in the next couple of slides. Let's take a look at the concrete example. So here we are interested, our target variable is the statement whether an individual died before 50 or not. The pluses correspond to individuals that died too early, that died before the age of 50. The minuses correspond to the instances, the persons that lived beyond the age of 50. And every point here, also every plus and minus, corresponds to one instance, and that instance has two descriptive variables. First of all, the number of glasses of beer that a person is drinking per week, and on the y-axis we see the number of cigarettes that somebody smoked per week. So what you kind of expect is that if people do not smoke a lot of cigarettes and do not drink a lot of beer, then most of them live beyond the age of 50. For the people that are drinking and smoking a lot, they typically die before the age of 50. So that's what this example tries to express. We have seen a similar, let's say, setup when I was talking about decision trees. But now we have two continuous variables, D1 and D2, and we would like to predict the class. So what we try to do is we try to draw a line separating the pluses from the minuses in the best possible way. This, of course, is not always possible. Suppose that this would be the best possible line separating, let's say, the people that die young and the people that live long. Then this regression line is making 3 errors. So that's the plus here. So this was someone that was not drinking a lot, was not smoking a lot, but still died before the age of 50, having a plus. These are two cases, this minus and this minus, are two examples of people that live beyond the age of 50, although based on their cigarette and beer consumption, you would have expected that they died before the age of 50. Such a line can again be described by let's say, taking the product of two vectors, the weight vector and the vector with the values for the various descriptive features. So let's, rather than writing this vector, I could also write the expression complete. So we have W0 times D0. And note that by convention, we say that D0 is equal to 1, something that I explained earlier. Then we have W1 times D1, W2 times D2, and we are looking, let's say, for the values, when we take a look at this product, that is equal to 0. So let's show, let's say, a concrete example. Let's assume that W0 is equal to 60. Note that we can describe the same line by, let's say, different weights by multiplying all the weights with the same positive or negative number. So we can simply say, okay, let's assume that, and we are not excluding any solution, let's assume that W0 is equal to 60. Then if we would like to fit the red line to go to this point 0, 20 and 30, 0, then these are the weights that we need to pick. And if we fill out these weights in this formula, we get this. So we have 60 minus 2 times D1 minus 3 times D2. Let's just check whether we are really describing this red line. If we take a look at this point here, so that is D1 is equal to 0 and D2 is equal to 20, then we have 60 minus 2 times 0 minus 3 times 20 is indeed, so we have 60 minus 3 times 20 is indeed equal to 0. So that's correct. The line is going through this point. We can also take a look at this point. So now D1 is equal to 30. So this value is equal to 30. And the D2 value is equal to 0. And then we have 60 minus 2 times 30 minus 3 times 0 is indeed 0. So this expression is indeed describing this line. And given this line, we can now talk about this product not being precisely 0. We can look at it, what is bigger and what is smaller, and that is corresponding to, is this above or below the line. And so in this particular example, with these particular weights, the product WD is negative if we are above the line, and the product is positive if we are below the line. So you can find that by filling out, let's say, some example values. So here I fill out I can fill out different values, and I can indeed see that that is the case. The difference between these two slides, I should explain this very carefully. Here we have 60 minus 2 minus 3. Then I switch to the other side. So here you can clearly see that these, if we have 10, 10, that indeed leads to a value bigger than 0, and that indeed corresponds to minus. If we have 30, 30, we are here, and then this expression leads to minus 60. That's clearly above the line. So above the line has a negative value, below the line has a positive value. This is highly confusing. Why am I showing it to you in this way? Is that what is above or below the line and what is bigger than 0 or smaller than 0 is just a matter of convention, because what I could do, that is what is happening on the other slide, if I multiply everything times minus 1, then I get minus 60 plus 2 times d1 plus 3 times d2, etc. That is what is happening on this slide. And if you look at this slide, you will see that now the meaning has swapped. Yeah, so it still says exactly the same thing, but if we now look at the values 10, 10, and we fill that out, we have a negative value. So now if we are here, we have a negative value. On the previous slide, it would have a positive value. When I talk about positive, I mean at the value of this expression. If we have, let's say, 30, 20, we have a value of 60, which is clearly above 0. So now WD is positive if we are above the line, and negative if we are below the line. On the previous slide, that was exactly the other way around. Yeah? I hope that this helps you understand that this is just a convention, what is above or below the line corresponding to what is positive and negative. I realize that is highly confusing, but it is simply the way that it is. So using this ID, we can talk about above and below the line depending on what kind of conventions that we use. And now the basic idea is that we label our real data using values 0 and 1. So here on this slide we are using plus is equal to 0, minus is equal to 1. So we are using this convention. And now we say if W times D is bigger than 0, so if this formula is bigger than 0, then we predict 1. In other words, we predict a minus. So here we assume that if this value is negative, we are above the line. If the value is positive, we are below the line. So if this is bigger than 0, we assume that we are below the line corresponding to the class a minus is encoded as 1. So what is now essential to understand is that for every instance we have it's either plus or minus. If it's minus, we say the value is 1. If it is plus, we say the value is 0. So we label our initial data, the target variable, in 0 and 1. And the same is the case with our prediction. So we compute W times D. So then we decide, are we on one side of the line or the other line? If W times D is bigger or equal to 0, we predict 1, otherwise we predict 0. And what is now essential that you see is that we have our real target feature, and what the actual value is encoded as a 0 or 1. And we have a predicted value, which is encoded as a 0 and 1. And now we can simply compute the error as we did before. So that is listed kind of in these 4 statements that we see here. So if W times D is bigger than 0, then this applies. We predict a 1. And if the class is minus, and minus we also encode it as 1, we take the difference between 1 and 1, we square that, and the squared error is equal to 0. The same is if we take W times D is smaller than 0, then we take as the predicted value 0, and we have also encoded the pluses. So in our original data, the pluses is as 0, and then the squared error is equal to 0 minus 0 to the power 2 is equal to 0. Now we look at the situation that W times D is bigger than 0. Then this leads to the value 1. And we have a plus. And then plus is encoded as 0. We take 1 minus 0, take the square of it, and that's equal to 1. And it's the same here. So the top two, let's say the labeling in the real data and being on the right side of the line kind of coincides. Here it is conflicting. So here in this third line we are predicting that the class is minus, but the predicted class in reality was plus. Here we predict that it is a plus, but in the real data it is a minus, and then we have an error. So this is the basic idea. So we have transformed this classification problem in a problem where we can still, let's say, talk about the sum of squared errors. So this is an example of the book that is using this principle. So we have two variables. We have a target variable which is good or faulty. So faulty is indicated by these triangles, good is indicated by these pluses. And again, we need to use a kind of similar encoding as we had before. And again, let's say this is highly confusing because what we can do is that we can basically multiply everything times -1 or times 20, and these formulas still stay valid. So that's the same, let's say, characteristic that we had before. So let's assume that we have found this line based on minimizing the errors. Then we can first try to have to interpret this. So we can rewrite this to this. Note that I can multiply everything times -1, and then the meaning doesn't change, but the direction kind of changes. We can talk about below the line, that corresponds to this, and above the line, that corresponds to this. So below the line, we can fill out, let's say, two example variables. So if we take a low value for both, we have a positive value bigger than 0, and that corresponds to, let's say, below the line. So below the line is positive. If we are above the line, we get that situation if RPM and vibration are large numbers, then we will have a negative value, and if these large numbers are there, we are above the line. So it's very similar to what we have seen before. Now we need to choose again an encoding, and the encoding depends on what do we interpret to be above or below the line. So here, if we have a value bigger than 0, then it is below or on the line. And then we predict, let's say, this triangle that is equal to 1. That's what we see here. If we are above the line, we predict, let's say that's class plus, and class plus is encoded with a 0. So now for every instance that we see here, we have both the real value, being 1 or 0 corresponding to error or good, and we have a predicted value also corresponding to 1 and 0, and we can compute the error as before. Yeah, so that's what we can do. Now this diagram is, let's say, using this, let's say, a regression line that we have, but it's a plane because we have, let's say, two descriptive variables, and I'm basically plotting that. Note that in many of the plots that also will be there on later slides, the axes have been normalized, but that's not very important. So we can plot, let's say, this value using RPM and vibration, let's say, as input variables, and then we can compute the value, and then we can talk about being above or below. So if we look at this plane, we can talk about what is above 0 and what is below 0, and that corresponds to if we are above, we predict an error. If we are below, we predict that it is good. So this diagram is now showing the result of this expression. If we now look at we are kind of encoding this continuous variable into a variable that can have a prediction that can have only two values, 0 and 1. What we see here is, let's say, the product of W times D. If I now apply this, so if we are above the line, it's 1. If we are below the line, it is 0, depending what you consider to be above and below. Then we get this. So you can see that it is no longer smooth. For certain values, we predict that it's good, that if this value is below 0, then we predict it's good, otherwise we predict an error corresponding to a 1. So this is before, what I'm showing here is this value, it's very important, and on this slide I'm showing this variable. So after applying this rule, if it's above 0 it becomes 1, if it's not above 0 it becomes 0. And note that this renaming may be confusing. So this gives us, let's say, a sound basis to try to find the weights that are minimizing the error, because we can compare these predicted values with the real values. We can take the sum of squared errors and everything is as before. However, there is one problem. Remember my metaphor that I used earlier, like we want to find the global optimum by walking down. And this is no longer possible because the decision surface is no longer smooth, right? So if we are here, we do not know in which direction to walk because the error will be the same, let's say, in all directions. So it will be either 0 or 1, and I cannot see how to improve. So we would like to make this surface smooth in such a way that we can take again the derivative and use that as a mechanism to walk down to the situation that is minimizing the error. And this is the basic idea of logistic regression. So we want to compute, let's say, a global optimum where the error is minimized. We cannot do that in this very binary situation where the error is 0 and 1 and just looking at the neighbors, we see the same values everywhere. We make the surface smooth, and by making the surface smooth, we get ideas in which direction to walk to reach the global optimum. The trick that is being used, that's why it's called logistic regression, is that there is this transformation. So the x value is the value which is the product of w times d. So that is the value that we have been focusing on before. Before we made it very, let's say, binary, because if it was above 0, it was 1, otherwise it was 0, or the other way around. Now we make it smooth. So there is this formula, and this means that any value, positive or negative, is mapped onto a value between 0 and 1. So please take a look at the characteristics of this function. If we fill out 0, right, then we have 1 divided by 1 plus e to the power 0 is equal to 1, then we have half. If we have minus infinite, so a very small number, so minus 10,000 or something like that, then we are approaching 0, right? Because if we take a large negative number, then this number is growing, and that means that this number is getting smaller and smaller and smaller. So the more negative we get, the smaller this expression gets. If we go to plus infinite, we have the phenomenon that if we have a very large positive value, this term approaches 0, and we are reaching the value 1. So what these examples are showing is that we can have a variable on a domain from minus infinity to plus infinity, and we kind of squash it onto the domain from 0 to 1, where 0 corresponds to half. And this is visualized here. So negative values lead to a value close to 0. Positive values lead to a value close to 1. Values that are around 0 are mapped onto 0.5. And this way, like if we compare to the original situation, we had something very binary. So it was either below 0 or it was above 0. So we had something that had the shape like this, and now it has been made smooth. You may again wonder why does the formula look like this, and that again has to do with what leads to, let's say, nice derivative. So the derivative of this logistic function looks like this. But I will not go into details of that. So that's the basic idea. So before we had something like this. So depending on the value of w times d, we would either have 0 and 1. So something that is not smooth. And we have now converted this problem to something that looks like this. So we now have a value between 0 and 1. So the range is exactly the same as before, but the surface is now smooth. So again, if we look at this diagram, so the logistic function has a shape as what we see here. If we take a look at our original function, it had the following shape. So it would be a straight line here until 0, then it would go to 1, and it would go like this. So this would not really work in our setting. If we would like to walk downhill to find the solution with the minimal error. So if we apply that to the example, then this is the expression w times d, and that leads to this, and now I apply it to this formula, and this is what we see. If we are around 0.5, these are the settings where we are not sure. for if we are, let's say, far away either in the positive or the negative direction, we are more sure. So this value between 0 and 1 can also be seen as a probabilistic expression. And so if we apply that to this example, whether the target feature is faulty can be seen as a probability that corresponds to this value between 0 and 1. And so if this let's say prediction is equal to 1, we are very sure it is faulty. And if we are very sure it's faulty, we are also sure that it is not good. Yeah? If this is a value, let's say close to 0.5, then we do not know, because we are very close to the boundary that we use to separate into faulty and good. And so the further away from the line, the more certain we are, yeah, in either direction. So this is showing some example values. So if we are close to the line, then this expression will evaluate to, let's say, values around half, and we are not so sure. If we move further away from the line, either in that direction or that direction, we are either sure it is good or we are sure it is faulty. Yeah, so that should be the intuition behind it. Now, if you look at the gradient descent process and we visualize it, we can see that basically exactly the same mechanism is being applied. So we have first, like we randomize, and then we have an initial regression line trying to separate it. Of course, we have a huge error here, and we try to reduce the error using the surface that is now smooth to walk down our mountain to minimize the error. You see that in every step the error is being minimized, and this shows the evolution of the error using the metric that we also used before. So in summary, I explained you logistic regression. It is very different, at least the way that it looks. It looks very different from, let's say, the normal linear regression, where the target value is also continuous. Now our target value is categorical. We only looked at a binary classifier. We would like to find the line which is separating, let's say, one class of instances from the other class of instances. And we do that by trying to find the line that minimizes the error. If we have a plus value, let's say, on the wrong side of the line, the error that we observe becomes larger if it's further from the line. So the things that are around the line, we are not so sure about that. So the error, if we make a mistake there, is not counted as high. I hope this gives an intuitive understanding of this notion of logistic regression next to the formulas that I showed. So we have now looked at the setting where we can have multiple descriptive variables. They can be continuous or categorical. If they are categorical, we can, for example, use one-hot encoding. We looked at the target variable. First, the target variable was continuous, and then we considered the situation where the target variable was categorical, having two values. So now at the end we have some, let's say, simple extensions that basically build on these basic ideas. So this is another set, and we now refer to the problem of looking at continuous variables both for the target feature and the descriptive feature. We only have one descriptive feature here. And what happens now if we have a relationship that is nonlinear? So I'm plotting here my let's say data used to train the model, and it looks like this. So now we can try to fit a regression formula, but we actually have a problem. right? Because we can try to draw many, let's say, straight lines, but it will not work. We will not find something that fits well with the data. So how to handle that situation? It is clear that there is a problem with the representational bias. The model that we're trying to learn can never fit this data, no matter how much we try to reduce the error. So what we can do now is that we can use the same linear machinery, as I call it here, but to pre-process the data to be able to fit, let's say, relationships that are nonlinear. And we do that by pre-processing the data. So here I'm transforming the data before I apply a linear regression. And because of the shape, I'm let's say, not just taking the variable rain, but I'm also taking the variable, let's say, the square of rain. So we have a constant, we have that it is simply transmitted on, and we have this. So if we now look at, we want to predict the growth, and we could now, if we want, like this W rain basically corresponds to the one value that was our D0 in the earlier examples. So this is in essence the same as before. So we have thus W0 times 1, nothing changed. This is our normal variable rain, taking directly the value. And the sigma 2 rain is like rain squared. And if you now look at this, you can see that you can fit functions of the shape, a constant times plus rain times a constant plus rain squared times some constant. And that means that we are able to express the functions that we are able to fit the curve that we have seen before. So we are able to fit now any second order polynomial, and again we can use the same strategy, trying to minimize the error, and what you now see is that in a couple of steps we are indeed, let's say, almost perfectly fitting our data set. So this is showing that it works. Of course, there is a bit of a trick here, because who tells me that this data can be fit by a second order polynomial? It may be that I need to use, I don't know, a logarithm or a square root or something else to fit the data. We will come back to that later. So the final model that we learn looks like this. Again, this is a constant 1. This is simply the amount of rain, and this is the amount of rain squared, and that leads to this shape that we see here. That was one problem, and I just explained it in terms of, let's say, having a continuous target variable. We can also do that for categorical target values. That's basically a combination of the IDs that I've presented before. And if I show that, so also here we have the problem if we want to separate, let's say, the triangles from the pluses. There is no straight line that we can draw that is doing a good job. But again, we can use this, let's say, pre-processing, and we can then fit shapes like the one that you see here. And if you look at the final situation, situation 5, this line is much better separating the data into, let's say, triangles and pluses than any straight line could do. So this is basically combining the two IDs. It is fairly trivial. Of course, you need to beforehand decide what kind of pre-processing you can do. So that was the situation that we cannot use a linear function, but we use pre-processing and then still are able to use the linear machinery. When we talked about logistic regression, we were always assuming that we have a target feature that can have only two values, true, false, plus, minus, red, green, or whatever classification we had. Of course, we also want to handle the situation where we have categorical data that do not have two values, but that can have 3 or 5 or 10 possible values that are not, let's say, ordinal, that are not ordered. So this is explaining a data set where, as a human, you can immediately see the structure. So we have here, let's say, two variables, spend and frequency. And we can see, let's say, the pluses correspond to the class family, the circles correspond to the class single, the triangles correspond to the class business. What you can clearly see is that based on frequency and speed, we can very well predict to which of the three classes a particular point belongs. But how now to apply logistic regression? Well, the idea is very simple, but I will not, let's say, explain you all the details. But the basic idea is that for every class, you try to apply logistic regression looking at that class versus all the other classes. So for example, if we look here, we are applying standard logistic regression where we have a binary classification, single versus non-single. And here we are not distinguishing between, let's say, family and business, if we look at the non-single class. We can also look at the situation business versus non-business, and remember that non-business could either be single or family, and we apply the same to family, and not family can be single or business. So we are applying three times, we are solving a logistic regression problem, and we get these three lines. Using the logistic regression formula, we also have an indication of, let's say, how sure that we are that something belongs to that class or not that class. And you can see that it is fairly easy, although the details, for details I refer to the book. It is fairly easy to then combine all of these results and pick the best scoring class. So that gives us the possibility to solve this. So again, if I show the, let's say, the evolution, we start with, let's say, 3 random regression lines using logistic regression. Then we iteratively try to improve each of these lines, and this is happening independently. Then that leads to this result that we see here. And then for every point we have kind of, okay, what is now the most likely class, single, business or family, and that leads to this separation that we see here. This should give you the idea of what we are doing. So I hope that this crash course in regression and logistic regression helped you to see that this is like a very generic approach of dealing with supervised learning problems, where the variables can be either categorical or continuous. What I think is also important to realize, and that's why I'm explaining regression that you have may seen in other courses before in a lot of detail. I'm explaining regression because it very nicely shows that we are trying to use an iterative approach to reduce the error. And later, if we talk about SVMs, if we talk about neural networks, for example, the back propagation in neural networks, it's in essence trying to do something similar. You start with an initialization. Based on the initialization, you can look at the derivatives. The derivatives gives you an indication on how you can improve, and then you iteratively improve until there are no further improvements possible. Regression is in principle most suitable for continuous features, but we have seen that we can also adapt it for categorical variables using logistic regression. In my next lecture, we will continue on this, and we will use let's say, a highly successful technique that is called SVM, and SVM stands for support vector machines. And the basic idea is very similar to logistic regression, as you can see here. However, the drawback with logistic regression is that if things are very far away from the separating plane, then that still has an effect on how this separating plane is running. If you look at support vector machines, the key idea is that if we want to find the separating plane, we are trying to find a line that is separating both classes, but let's say all of these values very far away from the separating plane and correctly classified, they should not influence this. So you can think of this as, okay, we are trying to separate these two classes, and you can just think of it, we have something in between and we inflate it as much as possible to separate things. This is a bit, let's say, the intuitive idea. It will be explained in much more detail, because SVMs are, let's say, a technique that is widely used in practice. So if you would like to read more, I used many examples from this book, particular chapter 7 and also things that were in the appendices. What is also good, although we are still, let's say, relatively early in the course, is to encourage you to start early on the assignment. Don't underestimate it. You may run into all kinds of technical problems. What is also important is that you use the interaction opportunities there are, and there are not that many, let's say, because the course is now given online. Please use the possibilities that you have to ask questions. Visit the instructions. These are the places where you can ask all the questions you want. If your questions do not get answered there, use the Q&A facility. But use these opportunities, otherwise at the end you will have difficulties understanding everything. This is showing, let's say, where we are now. So we just covered the 4th lecture on regression. We will continue with support vector machines. After that we will talk more about neural networks, evaluation mechanisms, before we go into the world of unsupervised problems.